My name is Rongzhi Zhang, and I would like to talk about the knapsack problem in this video. So let's go. So the overview of the knapsack problem is that a thief is robbing a safe with n items of different weights and values, and he has a limit that the knapsack could only contain a capacity of n, and he wants to take as many value, as highest value as possible. So in code, this becomes two arrays, one array of weights, one array of values, and a limiting capacity of n. And we want to find a subset of items that has a total weight that is less than or equal to the capacity, but returns the largest value. So before we go into this, I would like to talk about the difference between 0-1 knapsack and infinite knapsack. So 0-1 knapsack has only one copy of item, which means if we take that copy of item out, we can no longer take it anymore into our knapsack. But the infinite knapsack, which we are dealing with today, has infinite copies of each item, which means we can repeatedly take the same item over and over again into our knapsack. So the first way to approach this problem is, of course, brute force. But brute force has a lot of limitations. The idea behind brute force is to try all possible subsets of items. So as we know it, all possible subsets, there are 2 to the nth power such subsets. And in each loop, we add together the weights to see if they are larger or larger than the capacity. If it is larger, that means it is invalid because it just cannot take that many weights, right? And then if it is valid, then you add together the values. If it is larger than the current maximum, then you update the max. So let's see the time complexity. Adding together all the weights takes O of n, and adding together all the values take O of n too. So together, each loop takes O of n time, and we run it for 2 to the nth power loops, which takes O of n times 2 to the n time, which takes way too long. So we have to find another way to approach this problem. And another way, of course, is greedy algorithm. So there are two ideas of how to implement greedy. Either we could pick the highest value, or we could pick the highest value-weight ratio. But they are both not necessarily correct. Just think of this counterexample. When we have a capacity of 100, both ideas would let us pick the first item, which gives us a value of 99, but we do know that the optimal one would be to pick item 2 and item 3, which gives us a value of 100. So the greedy algorithm doesn't really work for knapsack problem. So we have to refer to dynamic programming. So for every dynamic programming as we know it, we need to have a recursive relationship between each problem and its subsequent subproblems. And for this one, we're dividing the knapsack into two parts, the last item and every item else. So the last item as we have it would have a weight of Wi and a value of Vi. And the other items would have a maximum capacity of n, which is the original capacity, minus the last item's weight. So at this point, what is the value we have in our knapsack? The value would be Vi plus whatever values these items are. So to maximize the value of a knapsack, we want to maximize the sum of these two, right? So that's how we derive this formula. We are taking a maximum of Vi plus the max value at capacity m minus Wi. And now we can see a recursive relationship, right? We are having max value at weight m and recursively to get max value at capacity m minus Wi all the way down until 0 when we cannot fit any item into it, right? So as long as we implement this recursive relationship with dynamic programming, we could get a pretty good time efficiency on that. So let's look at this code. So first, we need something to store the max value because it is basically the core idea of dynamic programming. And notice how we're having m plus 1 in our array instead of n because we want to store the max value from capacity 0 to capacity m, which is actually m plus 1 instead of m. And this is a very common thing in dynamic programming to be noticed about. And then we look at the pseudocode. So in the pseudocode, we iterate through all the items in the list. And if the weight of that item is larger than our current capacity, then we disregard that item because we cannot fit that item anymore. If it is not, we want to look at the remaining capacity if we take that item into our knapsack. Then we want to calculate the max value we could achieve by the remaining capacity by looking at our array. So if that value is not in our array, then we have to recursively calculate it by calling find max value again. If it is already in the array, then we simply use it in this step by adding together the last item's value and the max value we could achieve with m minus wi. Then we update that with our current max and return max in our function. So now let's look at the time complexity of this function. So we know that we are only implementing n plus 1 data points, n plus 1 boxes in our array, right? Which is O of n. And how long will it take for us to calculate the value in each of them? We have to iterate through all the items in the list, which is O of n, to calculate each value. So together, it will take O of n times m time, which is rather efficient. So that is how dynamic programming helps to solve the infinite knapsack problem. And that's it for the video, and I hope you enjoyed it. And thank you so much for watching.